Welcome to Physics Made Easy channel. The topic that we shall be covering at present is distance of closest approach. And before that, I want to clear some concepts. One is we have just done Rutherford experiment. In Rutherford experiment, we have got this experimental arrangement. Here, source of alpha particles. I will take this diagram. Here, source of alpha particle inside lead cavity. It is collimated by the collimator. Alpha particle is made to fall on a thin gold foil, and alpha particles are scattered by the atom, and their intensity of scattered alpha particle is measured by a rotating detector, which is made up of zinc sulfide screen. And what was concluded that most of the alpha particle they pass straight. It pointed to the fact that most part of the atom is empty, and then only one alpha particle among 10,000 or 8,000 retraced its path. Means the there is a, as the alpha particle retraces its path, it is pushed back on the same track. So it means it is colliding with a very heavy body. It is colliding with a very heavy body. So we concluded that in the center there is a heavy body which is positively charged, which repels the alpha particle. And there were some important collisions. As the angle increases, as the angle of scattering increases, the number of alpha particles scattered goes on decreasing. And the next part here, ray number 1, it hits the atomic nuclei, which is very heavy, and it bounces back and retraces its path. Means atomic nuclei is positively charged because alpha particles are positively charged, and atomic nuclei is much heavier than alpha particle because alpha particle has bounced back. And 2 and 2 dash, these two are the other alpha particle paths, and they are scattered at an angle like this, less than 180. And then 3 and 3 dash, they are the alpha particles which are scattered at an angle less than 90 degree. R0 is the distance of closest approach. Closest approach means this particle starts from here. At this point, whole of its energy is kinetic. When it approaches, kinetic energy gets converted into potential energy. At this point, whole of kinetic energy is converted into potential energy. And then potential energy is positive, it is repelled back. So this is how do we explain R0 is the distance of closest approach. Now, number of particles scattered is inversely proportional to sine 4 theta by 2, where theta is angle of scattering. Now the next thing that I shall be doing is the distance of closest approach. Distance of closest approach, that is, we are trying to find the size of the nuclei. Now, the distance of closest approach is the minimum distance from nuclei up to which a high energy alpha particle traveling head-on towards nuclei can move before coming to rest and then retracing its path. Now, this concept of distance of closest approach, it works under some Assumptions. 1. Scattering is the result of elastic collisions between nucleus and alpha particles. Nucleus and alpha particles are assumed to be point charges. Atomic nucleus is so heavy that its motion during the impact is neglected. So we have neglected the motion of the atomic nuclei during the impact. Now, let us focus on this diagram. Alpha particle is helium nuclei. It has got, alpha particle has got helium nuclei. It has got +2 charge, alpha particle. So we sometimes write it 2 helium-4, and this is positive. It has got positive charge +2e. This is the positive charge on alpha particle +2e. Now here, repulsion is 0. We assume the distance from ZD is very large. So repulsive force is negligible. It means potential energy is approximately equal to 0. These alpha particles, they are bombarded on the atom and thereby nuclei. So it means they will have some initial kinetic energy which is equal to half mv square. As the particle comes closer and closer, its kinetic energy is converted into potential energy. At a particular point at a distance r0, which is known as distance of closest approach, whole of the kinetic energy is converted into potential energy. Potential energy at this point, PE, will be equal to Q1, Q2. Q1 is this ZE, charge on atomic nuclei, and charge on alpha particle is 2E. This divided by R. And then we have got, here is K, where K is constant. I will write here K. If we put the value of K, then we get this is R0. This is Z into 2E divided by 4 pi epsilon naught R. So this is the potential energy. Whole of this kinetic energy, half mv square, gets whole of the kinetic energy at A becomes potential energy at B. So now we shall be putting these two values equal. So now I shall be simply writing half mv square here, half mv square. It's quite easy, even we can here space is not available, so I will just use this side and change the color. Half mv square is the kinetic energy at A. Half mv square. This is equal to potential energy at B, ZE into 2E divided by 4 pi epsilon naught R naught. From here I can calculate the distance of closest approach R naught. Now this distance R naught is equal to, now we can even cancel out this 2 pi. The distance R naught is equal to 2 Z E square This is 2ze square divided by m v square epsilon naught, and pi will remain there. Pi will be there. Now, if pi will be there, then 2 will also be there. This 2 will cancel with this 2, and distance of closest approach R naught becomes z e square divided by pi epsilon mv square. So this is the distance of closest approach. Another concept is the concept of impact parameter. Question on this has been asked in NEET. Impact parameter is defined as the perpendicular distance of the velocity vector of alpha particle from the center of the nuclei. Now if this is the alpha particle, let us assume this to be the alpha particle. I have deliberately made its sides larger. This is the velocity vector of alpha particle. This is the central line of the nuclei. This line is central line of nuclei. Central line. Now what is important is this distance from here is b, and when it approaches, alpha particle gets scattered at an angle alpha, like this, and this goes at an angle theta. Alpha particle is scattered at an angle theta. So this b is the distance of the velocity vector. Let v be the velocity. This is the velocity vector at a distance b from the central line of the nuclei, and this is the nuclei. We have deliberately drawn nuclei to be very large, and so obviously kinetic energy, so we have no derivation of the expression, so we shall be just discussing it theoretically. So this is impact parameter, this is the angle theta, and here the kinetic energy of alpha particle at this point is half mv square. And after doing calculations which are beyond the scope of your syllabi, the value of impact parameter is this. B is equal to 1 by 4 pi epsilon z square cot theta by 2 divided by E. Now, kinetic energy of alpha particle is large, impact parameter B shall be small. For same deflection, the kinetic energy of alpha particle is large, the impact parameter B shall be small. For same energy, here E, this is E. E is basically kinetic energy, remember. This E is basically kinetic energy. This E is kinetic energy. So what is important is impact parameter is inversely proportional to kinetic energy. First thing. And now if impact parameter is small, if B is small, then cot theta by 2 will be small. Listen this logic. If B is small, then cot theta by 2 is small. Therefore, scattering angle is small. means alpha particle passing closer to the nuclei will suffer large deflections. Will suffer large deflection. Again, if B is small, it means cot theta by 2 should be small. Cot theta by 2 is small for large values of theta. It means why? Because cot theta is cos theta by sin theta. So sin theta comes in denominator, and the value of sin theta is large for large angles. Or simply remember, the value of cot theta is small for large angle. If particle is closer to the nuclei, see this diagram. If particle is closer, let it to be coming like this. It means impact parameter is small. This is the impact parameter. This will be the impact parameter in that case. It is small. Now, B is small. If B is small, this implies from this relationship that cot theta by 2 is small. Cot theta by 2 is small. Cot theta by 2, if this is small, this directly implies theta is large. So this we conclude from where if cot theta by 2 is small, even we can say this implies B, this implies that B is small. If we take it like this implies that B is small. Or I will just conclude from here. That seems to me a better way of doing the same thing. If cot theta by 2 is small, if this factor is small, cot theta by 2 is small, it means B is small. B small means cot theta by 2 is small. Cot theta by 2 small means theta is large. It means alpha particle closer to the central line of the nuclei, they are deflected by large angles. And now let us proceed to the next part. An alpha particle traveling directly towards the nuclei will retrace its path, because in that case B will be 0. If alpha particle is along the central line, then obviously this B will be 0 in that case. B will be 0. Now I want to change the color. Now, if B is small, if B is 0 here, from the previous expression, cot theta by 2 is 0. This implies theta is equal to pi. Therefore, an alpha particle traveling directly towards the center of nuclei will retrace its path for large values of impact parameter B. Now, if B is large, cot theta by 2 is large. If cot theta by 2 is large, now we will follow the same logic. B large, this implies cot theta by 2 is large. If cot theta by 2 is large, This implies theta by 2 is small. Simply. So what is important is B is inversely proportional to theta, or theta is inversely proportional to B. Smaller the impact parameter, larger will be the value of theta. Larger the impact parameter, smaller will be the value of scattering angle. Now here we have shown the trajectories. The shape of the trajectory of the scattered alpha particle depends upon impact parameter. As impact parameter becomes large, angle of scattering starts becoming small. Here, at zero level, this is the target nuclei. Note, this is the target nuclei. Here is the target nuclei. This is the target nuclei. Alpha particle hits here and it retraces its path. Angle is 180. In this case, angle less than 180. Now B is becoming large. In this case, angle is just larger than 90 degree. As B is becoming large from 0 to 2.5 and then 10 at 20 bar. At 20 bar, this scattering angle is less than 90 degree. So what we are observing, as B is increasing, that is impact parameter increasing, scattering angle is decreasing. Here impact parameter is 100 barn. Barn is a unit of distance. Impact parameter is 100. If impact parameter is 100, here theta has almost, scattering angle has almost approached 0. So what is important is scattering angle is inversely proportional to theta. With these words, I finish this lecture, and we will again meet in the next lecture, in which we shall discuss Rutherford model of atom.